proof by contradiction is different from what we typically think about when we're dealing with proof. Usually you use the mathematical principles we know, algebra and axioms, theorems, in order to go from something we know to be true to something else that must be true. Proof by contradiction works in a different way, in that you assume that what the statement is saying is false, and then given that that is false, you try to find something that some other mathematical principle that is violated by that statement being false. So let's actually see an example of how we would go about doing this and use the steps of proof by contradiction to do it. So here's our statement that if the integer n is odd, then n squared is also odd. And so here's the idea. Let's try to see if this must be true. If I have an integer n, let's say n is 3, then 3 squared, which is 9, is also odd. 5 is odd, and 5 squared is 25. So it looks like this might be true. But let's look and see if we can prove this by contradiction. And so what that means is, let's assume that this implication is false, meaning that we have an n that is not odd, n that is odd, and an n squared that is not. Okay, specifically meaning that n squared is even. So let's say that this is the case. So n squared is even. This means, supposing this is true, that n squared is going to be 2 times something. We can say, let's say some constant c. And we know this because any even number is a multiple of 2 and some other number. This is the idea of this. So this means that n times n is equal to 2c. That's what squaring means. The other thing that we need to say about this is that c is an integer. So if we have an even number, then it means that the number can be written as 2 times some integer. 9, we can't do that because 9 is 2 times 4.5, and this is good because 9 is an odd number. On the other hand, if we have 26, 26 is 2 times 13, and that is an integer. So this is what we're looking to do. So let's look at what this statement says. N is an odd number, and clearly, since we're multiplying n by itself, we must also have an odd number. So on the left side of this equation, we have 2 odd numbers multiplying together. But we know that on the right-hand side, this is an even number. So on the left-hand side, we have an odd times an odd, and on the right-hand side, we have an even number. We can see that this will never happen. We can't have 2 odd numbers multiply together to get us an even number. This right here is the contradiction. This can't happen. And so our assumption that n is odd, but n squared is not, must therefore be false. And so in doing this, we are proving the statement, therefore, that if n is odd, then the original statement, and I'm going to write the 3 dots to indicate therefore, n squared is also odd. Let's move to another question now. This is a famous proof that we're about to do to show that the square root of 2 is irrational. So remember the idea here. We have to assume this is false. Okay, so what this means is we have to assume that square root of 2 is rational. Let's think for a second about what that means. If square root of 2 is rational, it means that square root of 2 can be written as the ratio of 2 numbers, p and q. And p and q are integers. And we know q cannot be 0 because it's in the denominator. There's one other thing that we need to assume here, which is a little hard to see, but the idea is that if this is rational, p and q also can't have any common factors because they would divide out when they were put in the fraction. So the idea behind this one is that p and q, p could not be 6 and Q 9, for example, because 6 is 3 times 2, and 9 is 3 times 3, and those two numbers have a common factor of 3. So we could not use this as an example. So P and Q can't have any common factors. Here's how the proof works. If the square root of 2 equals P over Q, we can square both sides and see that 2, therefore, is going to be P squared over Q squared. We can rearrange this to say that P squared is equal to 2 times Q squared. This means, similar to what we had in the previous proof, that this is an even number because this is 2 times some other number. That's our definition of even. So this means that P has to be an even number because we can't have P squared be even and P be odd. So if P squared is even, that means that P is an even integer as well. And so one way we could write this is by saying that P is equal to 2 times some integer, we'll call it K. This is the same way that we defined even numbers in the previous example. Substituting this in, this means that P squared, which is 4K squared, must be equal to 2Q squared. So Q squared, rearranging this, is therefore equal to 2K squared. And this means that Q is an even integer. So both P and Q are even. And if P and Q are even, that means they have a common factor of 2. Now, I want you to see if you can identify the contradiction here. This statement says that P and Q have no common factors, but we've just shown that P and Q have a common factor of 2. This is the contradiction. And so because this is a contradiction, then our original statement must be false. So this statement up here where we said it's assumed that square root of 2 is rational is not true. Therefore, square root of 2 is not rational. And that means that square root of 2, therefore, is irrational. We've proven the statement. All right, one more example to do. This is going along with our theme of even numbers. So if n cubed plus 5 is odd, then that means that n is even. So remember this idea, n being even means that n can be written as 2 times some integer, some constant, something that goes right here. So this is our statement. We want to assume that this is false. And so the way we do that is, let's assume then that n must be odd. So let's think about what that means. This means that we can write n as an even number, let's just say 2k plus 1, where k is an integer. Now I keep writing k as an integer. We have a faster way to do this. We can just write that k is in the element of the integer set. So that's the way that we say that. So n equals 2k plus 1. Let's now write n cubed plus 5 using this statement. So we've substituted this expression for n. Let's expand that using what we know about cubing a binomial. All right, and let's continue simplifying. And I'm now going to see that there's a common factor among each of these terms, and that common factor is 2. So I'm going to factor out 2 from everything. And so hopefully at this point you're starting to see the pattern that with that 2 out front, this is 2 times some integer that n cubed plus 5 is equal to. And so we have just shown that n cubed plus 5 is equal to 2 times an integer, which means that n cubed plus 5 is even. Here is our contradiction. We set up here n cubed plus 5 is odd, and now we've shown that n cubed plus 5 is even. That is the contradiction. Therefore, we can use the hypothesis of the statement that n cubed plus 5 is odd. If n cubed plus 5 is odd, that the conclusion of that statement is true. And so that's the idea of proof by contradiction. You assume that the conclusion is the reverse of what the statement says, assume it's false, and then search for a contradiction somewhere using just algebra or other concepts to show that there's a major flaw, a major contradiction that results from that conclusion, which then lets you say that this statement is true. This is proof by contradiction.